Thank you. Okay, well, thank you very much for the opportunity to speak here. I think it's a great honor and pleasure to be in this conference, and also it's also good for ICTP and ICTS to work together. We are working together in several activities, and I'm like to congratulate Spenta for putting all this effort to create ICTS and all his colleagues, and it's good that this is a way to start this new era for this institution. So what I'm not very thankful about the organizers is that they asked me to speak after Nima. So because whatever I say will be the low point of the session. So anyway, and it didn't help that I chose a title which is a little bit negative. So it's a string compactifications and low energy supersymmetry, the last attempts, but I put a question mark. The question mark is always a way to say that whatever the standard joke that the answer to all the titles with question marks is no. So it may be not. So this is work I have been doing in collaborations with the combinations of these people: Aparicio, Chiccoli, Duta, Clever, Skribendorf, Maharana, Mayhofer, Milla, and Valandro. And it has been published in these 3 papers, the most recent one earlier this year, and there will be more to appear. So essentially the idea is to take some concrete string model scenarios and try to push it to the end to test with any experimental constraints. So we'll see how far we can get. So you don't need a reminder, but just to be complete, the low energy SUSY from the bottom up, recall the motivations for the good things about the low energy supersymmetry, the hierarchy problem, gauge coupling unification. They have a concrete candidate for WIM dark matter, and radiative electroweak symmetry breaking, which is a nice way to get the Higgs potential to get to the non-zero wave. From the top down, supersymmetry breaking in 4-dimensional strings. It's good that we have concrete, very well understood Calabi-Yau compactifications with n equals to 1 supersymmetry. It's actually, we are celebrating now the 30th anniversary of the classic paper of Candela, Sorbes, Strominger, and Witten from Calabi-Yau compactifications, and it's very healthy and very active in the field of string phenomenology. Then there are issues, which are mostly model stabilization and supersymmetry breaking. Some progress has been made in the past 10 years or so. Still, we need much better understanding. And for that, I can just emphasize the fluxes with in the GKP paper, the Giddens, Kashu, and Polchinski. Number 2 additive effects that people have worked for the years on the kind of racetrack potentials. And anti-branes introduced by KKLT to do the uplifting in the model stabilization to get the jitter. And also breaking supersymmetry by the anti-branes. So, as you've heard from Nima, we have the current situation. We have to accept that 10 to the minus 2 or 10 to the minus 3 fine-tuning and see it as a natural. Or we can just see other options that extend the MSSM, address the hierarchy problem in a different way within supersymmetry, like a tune an MSSM, split supersymmetry, as Nima just described, or even large supersymmetry breaking scale. So people have been working on these ideas already for the last few years. Even, of course, we have to consider non-SUSY approaches to a hierarchy problem. And since we don't know what to do and we are kind of lost after the Higgs discovery, there's a golden opportunity to use string scenarios as a guidance to look for beyond the standard model. So let me just remind you, the string phenomenology as a field, we have a long-term goal, which is very ambitious. String theory scenarios that satisfy all particle physics and cosmological observations and hopefully lead to measurable predictions. And as you know, people have been working for the last 30 years on making progress on this. So we have even the conference every year, the 14th conference happened 2 weeks ago in Madrid. And it's an active field where some progress has been made slowly, but over the years, some concrete progress. So what we look for progress is a generic model-independent results. That would be the ideal thing, and that people have tried. Then you have to go explicit constructions of classes of models, and try to explore what the implications they have, and do explicit computations for the effective field theories. That's a big part of the challenges. And from there, try to extract scenarios that can lead to eventually testable predictions. So that's the goal. We know from the generic case, the generic four-dimensional strip predictions, the standard ones, supersymmetry, small representations, branes, fluxes, no global symmetries, etc., actions. The one I want to concentrate today is this cosmological moduli problem, CMP, which it appears whenever you have supersymmetry broken and model stabilization at the same time. And in that case, we know that there is a problem if the mass of the moduli is heavier than 30 or more TeV. So since it will be an important part of my talk, so let me just describe it in more detail. So at the end of, during inflation, the moduli are sitting in a minimum, not necessarily it's a zero temperature minimum. After inflation finishes, start oscillating and dominate the energy density of the universe because it's a redshift like a matter. And so it dominates the energy density of the universe. And at some point, when the Hubble constants of the order of the mass of the field, then it goes back to the minimum. And in the meantime, it reheats, and that's essentially what produces the standard model particles. Essentially, that's the reheating. So actually, the reheating after inflation may not be the source of our own reheating, but it may be the reheating due to this decay of this particle. And that's where the constraint comes. So the reheating temperature has to be heavier than 1 MeV to not ruin, say, nucleosynthesis. So the mass of this field has to be more than 30 TeV. And so the problem has been with us for many years already. So it was found in the polonic fields in supergravity in the 1980s, then proved in the 1990s to be a general property of string models whenever you break supersymmetry and stabilize the model at the same time. So this is over all these years, nobody has found a good solution of this problem. So one attitude will be just to take it seriously as a consequence of string theory and try to use it as a principle to follow, as a guidance. Okay. So for a string scenario, the challenges are you have to have, well, the concrete explicit unequal band compactifications, concrete SUSY breaking mechanism, model stabilization with a small cosmological constant, and avoid the cosmological model problem. Chiral visible sector and computable soft terms. At the end of the day, we have to be able to compute the soft terms. So for model stabilization, we have the standard thing, just a Calabi-Yau with 4 cycles and 3 cycles. That the 3 cycles are stabilized by fluxes as a GKP, and the 4 cycles have to be stabilized by some other effects, usually non-perturbative effects. And for that, we have concrete scenarios. In type 2B or in general F theory, there's the KKLT, there's this large volume scenario that we have been developing over the last few years. Of course, in type 2A, heterotic and G2 manifold, these are less under control for this model stabilization. And for my talk, I will concentrate on this large volume scenario. So the idea of the large volume is that essentially you have a superpotential determined by fluxes that fixes the sizes of the 3 cycles on the dilaton, and then perturbative corrections to the carrier potential for the moduli, for the carrier moduli include the 3-level and leading ordered alpha prime corrections, include the non-perturbative effects for the superpotential, plug all that in the scalar potential, and then you have several terms depending on your power on the volume. You use the volume as the expansion parameter. So this is 1 over the volume square coefficients, this is 1 over volume cube, and higher order powers. The 1 over volume square, the term fixes the dilaton and the complex structure moduli, as I said before, like GKP. And then we are left with this other part for the carrier moduli. And in this part, you get, using the alpha prime correction that determine this term, you get a volume to be e to the a tau, with tau is 1 of the cycles. And the tau fixed to be 1 over the G strain to be greater than 1. So that means that the volume is exponentially large. So that's the basis of the large volume. The interesting thing that is in contrast with other scenarios like KKLT, the minimum breaks supersymmetry. So supersymmetry is already broken, and the source of supersymmetry breaking are the fluxes. Yes, and in the simplest case, you get anti-de Sitter. To get a large volume, we need general conditions, which are that the Hodge numbers H11 has to be greater than 1 and smaller than H12. So that happens for half of the Calabi-Yau. So this is a very, very generic kind of a scenario to fix the moduli. And it uses the generic values of the fluxes, like fluxes between 0.1 and 1,000 are the natural values. And that's, for instance, for a typical Calabi-Yau that people have considered. And essentially, each point here is a solution of the complex structure moduli. And they give you essentially points in that value of range of value of the W0. Okay. To go beyond that, you have to have concrete models with everything included, not only the moduli, but also matter fields. And this is a probably complicated picture, but essentially it's a cartoon of a Calabi-Yau, where this is the high cycle, the big cycle, this is the small cycle that helps for model stabilization. Then you have the standard model located in some other cycles. Usually happens to be at D3 branes at singularities. But it can be also D7 branes and so on. And on top of that, then you have matter fields, and then your potential becomes more complicated, and you have to do all your work to do the model stabilization. So, so you need to do concrete Calabi-Yaus and compact Calabi-Yaus, of course, with including chiral matter. And for that, we have done that in this paper, where you have a fully supersymmetric effectivity theory, all geometric moduli stabilized, and with chiral matter. And the volume happens to be moderately large. This is only 10 to the 6, 10 to the 7. We cannot get beyond that for some reasons. And it is of what we call sequestered scenarios, in the sense that the standard model cycle collapses to 0, so that means that the branes live at the singularity, and the F term of that cycle is also 0. So supersymmetry is not broken on the observable sector, but it's broken far away. So the F term of the scalar potential takes the general form I was telling you, plus extra terms coming from the matter fields. And these extra terms from the matter fields, in this particular case, happen to be positive, and they lift the vacuum that you can get close to 0 cosmological constant, so to the sitter. So in that sense, you can add the anti-branes as a KKLT dude, but you don't have to, because this is enough to do it. I have to say that this is a subject of recent debate. So notice that here we get the sitter, but in a way that is only an effective field theory perspective, so much has to be done or learned from this. Now the relevant scales. The string scale goes, you have to trace the power of the volume to the minus a half, in this case. Kaluza-Klein volumes to the minus 2/3. Gravitino mass is one of the volume, but this is something that is makes this case very non-generic. The mass of the volume modulus is smaller than the gravitino mass. So this is a non-typical situation that people see in supersymmetric theories, where you expect that all the splitting of the multiples or the masses would be afforded the gravitino mass. In this case, these moduli are lighter than the gravitino mass, and they happen to be protected even by loop corrections and so on. So we cannot raise the value of this scalar masses. So usually they have non-generic implications, in the sense that what people usually assume when you talk about supersymmetry breaking in string theory is that the moduli masses, since they are given by supersymmetry breaking, they are of the order of the gravitino mass. They also assume that the soft terms are of the order of the gravitino mass, and identify the gravitino mass with 1 TeV. So this is the standard law, and what essentially most people do. In this case, when you are concrete and explicit, you happen to find a different scenario, a different picture, in the sense that the volume modulus, as I say, is much lighter than the gravitino mass. And since it is much lighter than the gravitino mass, I remind you about the cosmological moduli problem that I mentioned before, is more acute than expected, because it's even, since it is lighter, and this has to be heavier than 10 TeV, that means that the gravitino mass has to be much heavier than that. And then we can ask, what is the structure of the soft terms for the chiral matter fields? So this is the challenges. Let me take something to drink. Okay, so And for this, we use the effective field theory, the superpotential for the matter fields. They have the Higgs part and the matter fields, the Carrier potential for matter fields. You span in powers of the corresponding matter fields, the Higgs part, and plus dot, dot, dot. This part is not well understood and not well computed, so that's one of the challenges people have. And the best we have found to do is to use an indirect argument by scaling, in the sense that the Yukawa couplings have this general form in supergravity. We know that the holomorphic part of the Yukawa couplings do not depend on the T field. By locality, we expect that these ones should not depend, at least to leading order, on the volume. So we know that depends on the volume on the Carrier potential for the moduli. So from that we can extract the structure of the Carrier potential for the matter fields. And then it has to be e to the k over 3, so just to cancel this part. If it is times a function of the S and U fields, that is not known. Of course, this is only a leading order expansion, so we can have plus dot, dot, dot. So we separate the models into two classes. If this is approximate, we call it local, and if this is exact, we call it ultralocal. And that will give us two different scenarios for supersymmetry soft terms. So SUSY breaking. The fluxes break supersymmetry. This is the source of breaking of supersymmetry. In the effective field theory, the F terms of the Keller moduli, in the sense that they break supersymmetry, plus the dominant of S and FU. As I told you, the F terms of S and U are 0 to leading order. They don't break supersymmetry, like in GKP. However, when you have to go to higher orders, they will be you have to compute the next to leading order contributions of this, and they will be non-zero in general. So they can contribute if there are cancellations in the case of the Carrier moduli. And the standard model can be lived on the D3 or D7 brane, and that gives rise to several scenarios. So essentially, we can have a standard model living on a D3 brane at the singularity, or the standard model living on a D7 brane wrapping a 4-cycle. And then you can have hidden sectors at the singularity, or hidden sectors also with D7 branes wrapping 4 cycles. So there are several scenarios because of that. So in that sense, if you have the standard model here, then the F term of this cycle doesn't break SUSY. So the only way that this knows how the supersymmetry has been broken is by the F term of the cycles corresponding to faraway cycles. So that means that they have to communicate through a volume correction. Thank you. And then that means that that they will be suppressed. So that means that the soft terms here will be much smaller if supersymmetry is broken farther away. And this is the structure we have. In general, 5 different scenarios that we find from the. In this scenario, we have so W0, most of them are further 1, except for this one. And so you can see that you want here the entry half is 1 TeV. Then to get that 1 TeV, so that's in the soft terms of the same order, that means that when everything is broken in the same place, then the string scale has to be much smaller than the God scale, and you have the cosmological modular problem. So that's not a very good scenario. On top of that, we haven't been able to realize it in a concrete model. So the second, you have also to tune a lot of the superpotential to get the TeV scale and the God scale to work. And so this mimics the KKLT scenario again, because it's, you have to have very small superpotential. It's not very generic in our case. And again, you have the cosmological modular problem, so it's not suitable. So the next 3 is the ones that I'm going to consider now. So I'm going to use the cosmological modular problem as a basis for the different scenarios. So for all of them, the string scale is 10 to the 15, W0 for order 1, M3 halves of 10 to the 10 GeV. And then you don't have the cosmological modular problem because the volume masses are much lighter than this 10 to the 10 GeV, but heavier than the 10 TeV. And in the first case, you get 10 to the 10 GeV, the scalars of terms. In the next one, you get 1 TeV, and the other one, you get 1 TeV for the gaugino masses. Both the scalar masses are heavier because this is a volume factor here. So that means that you have an example of a split supersymmetry. So in that sense, we have realized large scale, standard MSSM, and split supersymmetry in these scenarios. So for this talk, we'll consider mostly the sequesters of terms. And in that case, we have compute the Gaussian masses, the scalar masses, the trilinear terms, the mu and the b mu, and we computed them in terms of the gravitino masses and so on. So these are here. Therefore, the Gaussian masses are universal for all the different scenarios. I have local and ultra-local, as I described before. The scalar masses can be the same order of the Gaussian masses or bigger, depending on the scenario, and that's what gives us the split supersymmetry spectrum. And the trilinear terms, mu's and b mu's, are more or less universal. The coefficients here that have not been computed, sorry, the pointer is not working now. The coefficients here, C's, they are all functions of the fluxes. And in this sense, yeah. This is an interesting thing because then that is, if you want to do that, you have to do the tuning at low energies. You can trace it back to high energies and by just tuning of this coefficient. So tuning means choosing corresponding values of the fluxes that will give you the corresponding values of the C parameters. So in that sense, you have an explicit way of seeing how the tuning, quote unquote, will work. So as I say, we have to use the cosmology as a guiding principle. We use the cosmological model problem as the basic, as a guiding principle. So the constraints, that will give us constraints on what the values of the volume are, which is between 10 to the 3 and 10 to the 9. Thank you. And very good. And so that means that that will give us a range in general. So just using cosmological model problem without using anything explicit concrete, you know that the string scale is between 10 to the 17 and 10 to the 14. The gravitino mass heavier than 10 to the 10. The Gaussian mass is between 10 to the 2 and 10 to the 12. And then you get the reheating temperature, which is after the modulus decay, is very light. So 10 to the 7 to 10 to 1. So whatever we do, we cannot get heavier than 10 to the 7 GeV reheating temperature. So that will change the low scale picture. For instance, it's hard to get the leptogenesis from here, for instance. And the thermal history is different than the standard. This is the standard one, where you have a thermal dark matter, and in this case it's non-thermal dark matter because at some point is the energy density dominated by the modulus, and then you get the reheating after the modulus decay. So this is the picture we are having. And it's important that the modulus, when it decays, it produces the visible sector, but also produces axions and so on in the hidden sector, and that's dark radiation. And that gives us a strong constraint of what kind of models we can have.
questions, we close these sessions and we move to a break.
We're running a bit